Assalamu alaikum. In today's video, we are going to discuss the introduction of computing. Our reference book is the AVR microcontroller and embedded system using assembly and C++. In today's video, we are going to discuss the following topics: the internal organization of computers, the different part of computer, I/O, memory, CPU, and the connecting the different parts, for example, connection of memory to CPU and I/Os to CPU, and how the computer works. The internal organization of computer is consists of CPU, memory, I/O, the input and output devices. Input devices like keyboard, mouse, sensor, and output device, LCD, printer, hands of report, and etc. In memory, we have memory is those type of thing which can store, retain, and recall the information. Example is hard disk, piece of paper, and manual, etc. The following are the characteristics of memory. The capacity, like number of bits that the memory can store. Example 128 kilobits or 256 megabits. The organization, like how the location are organized. Example 1.128 x 4 memory has 128 locations bits each. Access time means how long it takes to get the information from memory. There are two types of memory, semiconductors and non-semiconductors. In semiconductor, the ROM, there are two types, RAM and ROM. RAM are like mass ROM, PROM, programmable ROM, EPROM, erasable programmable ROM, EEPROM is electronic erasable PROM, and flash ROM. There are three types of RAM, SRAM, DRAM, and NVRAM. The mass ROM is programmable by IC manufacturer, and PROM is OTP ROM, means one-time programmable. We can program it on only once. EPROM is erasable programmable ROM. It can be erased by shining ultraviolet radiation. Erasing time is up to 20 minutes. The entire content of ROM can be erased through UV radiations. EEPROM is electrically erased programmable ROM. These can be erased instantly, and each bit can be erased separately. Flash ROM. Erased in a flash, the entire device is erased at once. Now we'll discuss the RAM. SRAM is also known as static RAM. It is made of flip-flops, means transistor. There are two advantages of using SRAM. It is faster and there is no need of refreshing. The disadvantages of SRAM is that it's a high power consumption and it's very expensive. The dynamic RAM. It is made of capacitors. The advantage of using dynamic RAM is that it has less power consumption, it is cheaper and has a high capacity. Disadvantage of using dynamic RAM is that slower compared to the SRAM and need a refresh. NVR RAM means non-volatile RAM. It is made up of SRAM, battery, and control circuitry. Advantage of using NVRAM it is very fast. It is infinite program erase cycle. It is non-volatile, and disadvantages is that it's very expensive. Now we'll discuss about the internal part of computers. CPU. Task. The following task is being performed. It should execute instructions. CPU's main task is that it should execute instruction. It should recall the instructions at one after another and then execute them sequentially. This diagram shows the memory pin out of the CPU. Here we have the graph and the connection of memory to CPU. In this diagram, we can show the connection of I/O devices, means input and output devices to CPU, like the connection of mouse, keyboard, sound card, graphic card, networks to CPU. For this, it should have a lot of pins. In this diagram, we can show how the input devices up to n number are connected to CPU. Like one pin is connected to the address line of CPU, the another pin is connected to databus of CPU, and the last two lines of input and output devices is connected with read and write me control bus of CPU. And in this diagram, the input and output devices and the memory are connected to CPU through these connections. How it could be managed? It could manage number of inputs or address line and how it's going to be controlled on control bus 1. Now we're going to conversion. First we will convert the decimal number into binary. In example 0.1 we have to convert the number 25 to base 10 into binary means into base 2. To convert the binary into 10 we have to divide the number of base 10 by 2. If it has a remainder 1, it's going to be written on the remainder section of our answer. 20 like in this 25 is divided by 2. We have the answer 2 with remainder 1. So the question 12 is written on the question area, and the remainder 1 is on the right side. Now again that number 12 is divided by 2 and we have the answer 16 with 0 remainder. Again the quotient is divided by 2 and we have divided it to 2 until we get the quotient 0, unless our remainder is 1 or 0. Now 6 is divided by 2, have the quotient 3 with remainder 0. Again 3 is divided by 2, we have the quotient 1 and remainder 0. Now we are going to divide 1 by 2, which is quotient 2 with remainder 0. Now we have to now we get the answer on the remainder side, but we are going to write our answer from most significant bit to least significant bit, means from bottom to top. Therefore, the binary of the number given 25 is 11001. Here you can see the answer. Now we're going to convert the binary into decimal. To convert this, we are going to multiply a binary to the 2 to power 2 with multiple of 2. For example, we are going to write the number 11001 given in the question and then multiply by above, like 2 power 0 is 1, 2 power 1 is 2, 2 power 2 is 4, 2 power 3 is 8, and 2 power 8 is 16. Then these numbers are going to multiply with the given number respectively and having the answer 16 plus 8 plus 0 plus 0 plus 1, having the 25 with the base 10. And that's how we're going to convert our binary into decimal. In next example, we are going to convert decimal into binary. 39 to base 10 to binary. First, 39 divided by 2, we have the answer 16 with the remainder 1. Then 16 by 2, 8 with remainder 0, and 8 by 2 with to quotient 4 remainder 0. And again until we have the quotient 1, and at this point we have our answer, which is 100111 to the base 2. In next example, we are going to convert hexadecimal into binary and binary into hexadecimal. In example 0.4, we have a binary number and we have to convert it to hexa. In this, we have to group the binaries into up to 4 groups, up to 4 digits from right side. We are going to group this 1010 in one group, that 1111 into another group, and 1001 in third group. And then we are going to look at this table and write the respective binary of that number or hex of that number. For example, 0101 is 5, and its hex is also 5. We are going to 5 in downward 5. In second group we have number 111 and hex of that number is F. And 1001 is, and hex of that 1001 is 9. So, and that's how we can convert our hexa into binary into hexa with 9F5. Now we are going to convert hex into binary to 9B. For this, we are going to again look at this table and write the respective binary of that hex. For example, the binary of 2 is 0010. Look at here. Now binary of 9 is 1001 and binary of B is 1011. So writing the combine, we have got the binary of our number. Now we are going to convert the base 10 to hex. We have for this first we will convert the number into binary and then binary into hex. For example, for 45 we are going to convert the 45 into its hex. We get the number hex of 45 is 101101, and now we're going to convert this number into hex. First going to group in 4 1101, which is equivalent to D, as you can see in this table, and the binary and the hex of 0010 is 2, and that's how we're going to convert our number into hex. Now I'm going to convert 6 to 9 to base 10 to hex. For this, first we're going to convert to binary, and the binary of 6 to 9 is 10011100101. I'm going to group into 4. We get the hex of 275 by looking at this table corresponding binaries. And now again we are going to convert 1714 to base 10 to hex. First we're going to write its binary through the procedure we have learned before, and then going to convert that binary into group of 4s and then write it hex corresponding as shown in table before. Now we're going to convert the following hexadecimal into decimal. To convert hexadecimal to decimal, first we're going to convert it in binary and then into hex, then into decimals. The number given is 6b2 to base 16. First we're going to write its binary. The binary of 6 is 1001, B is 1011, and 2 is 0010. Now I'm going to convert this binary into decimal. 2 with here 2 raised power 0 into 0, 0. 2 raised power 1, 2 into 1 is 2. You can see here it's become 0, it's become 0, it's become 16 plus 30 into 1, 32. It's 64 becomes 0, 128 into 1, 128 plus 0 plus 512 plus 100, 1024, which is equals to 1714 to base. Now we're going to convert 9f to base 16 into decimal. First we're going to convert it into binary to writing its corresponding binary, which is equal to 100111100101101, and then adding all the numbers we are having up to 40,749 to base 10. Now we'll go discuss the serial and how we're going to add two binary numbers. In the example 0.8, we are going to add two binaries. Number one is 1101 and second number is 1001. First, we know the decimal of the number. The decimal of 1101 is 13 and 1001 is 9. And adding 13 plus 9 is 22. So we have the answer correspondingly 22. Now, look at this table, and now we're going to add the numbers up and down. 1 plus 1 is 10, 10. 1 plus 1 is 10. 0 on some side and 1 on the carry on the next number to be added. 0 plus 0 is 0 and 1, which is from carry, is equals to 1. Now 1 plus 0 is 1. 1 plus 1 is 10. 0 on sum and 1 on the carry. If there's no other number to add, so it goes directly down and having the number 10110 as the answer. Now in example 0.9, we are going to take two complements of number. Two complement number means flipping every entity or bit of the number and then adding 1 to it. For example, we have a number 100111101. Having its one complement means flipping all entries means 0110010, and then adding 1 is and having the two complement, adding 1 to 0110010. Answer is 0110011 is equals to 2's complement of a given number. Here is the ASCII table By using ASCII table, we get the binaries of the following instructions: alphabets, special characters, and some controls. Here's the abbreviations of control characters. For example, null. Its abbreviation is null. ENQ means equinary, ACK acknowledgement, BS backspace, HT horizontal tab, and many more. Here is another example of data address decoder. In this diagram, you're going to design address decoder to address the 300H to 3FFH. First, we are going to rewrite the address range in binary, then separate the fixed part of address, and then design the logic circuit. Now we are going to look inside the CPU. In CPU, we have PC, program counter, instruction decoder, ALU, arithmetic logic unit, you can see ALU, and registers. That's how it's going to connect. This is the memory, and these are the IO devices. First, we have the any entry from IO device IO component. For example, 9 is going to travel through and then going to store on register. As you can look at here, that 9 from IO 17 going to storage register. Then our another entity 5 from a memory unit can goes through these buses and they're going to store on register and up on top of the previous entry. That's how instruction decoder works. The first three, it's based on 8 bits. Our first 3 bits are OP code and last 5 bits are operand. In this table, you can show the operation code meaning. And here is example. There are two types of architecture, von Neumann and Harvard architecture. In first diagram, you have shown the Harvard architecture of CPU. Our memory from code travels to CPU through databus and data memory to CPU through databus, but it is in both direction from databus to data memory and CPU. Through address bus, data from CPU to memory code and data memory, and control bus is also goes from data memory to code memory. In bottom, you have just seen a von Neumann architecture. From this, you have seen the code memory, data memory goes uh, means CPU address from CPU goes to code memory, data memory through data bus, address bus, and control bus. But in data memory, it also goes from data memory to CPU. Now we are going to discuss the general purpose of microprocessor and microcontroller. Microprocessor is RAM, ROM, I/O ports, and chip itself. Example: Pentium, Intel, PowerPC, Motorola, Spark, Sun. Uh, um, its applications of using microprocessor is desktop, laptops, workstation, and servers. Microcontrollers are RAM, ROM, timers, I/O ports on a single chip. Like 8051 Intel, 68HC08 Motorola, AVR ATML, Z8 Zilog, PIC microchip, ARM advanced RICS machine. Applications are like TV remote control, video game, robots, and etc. Here is a block diagram of general purpose microprocessor and microcontroller. In the block diagram, you have seen the general microprocessor, and bottom you have seen the microcontroller diagram. In this, you can see the companies that produce 8-bit microcontrollers. In table 1.6, you have seen the company ATML, Microchip, Intel, Philips, Zilog, Delaz, Semi Maxim, and Freescale Semi, with its website links and architecture of them. In table 1.7, you have seen the comparison of 8051 and PIC 18 family and AVR 14-pin package diff comparison. Their program ROM, the data RAM, the EEPROM, the timer, the ICs between all of three of them. Now we'll discuss the embedded system. An embedded system is controlled by its own internal processor or microcontroller as opposed to internal controller. A PC is connected to various embedded products such as keyboards, printer, modem, disk, controller, sound card, CD-ROM, driver, mouse, and so on. The printer gets data and prints it. A mouse takes coordinates and sends it to PCs. Here are the examples of embedded products. In computing, PC, notebook, laptop storage, color printer, laser printer, modem, cable modem, copier, scanner, digital cameras. In cars, it can be used as anti-lock breakers, car bags, engine control, transmission control, climate control, collision avoidance, navigation, tip computer, instrumentation, keyless entry. In communication can be used as wireless phone, cellular phone, PDA, pager, fax machine, intercom. In cards, it's big like banking, electronic purse, security and tolls. In consumers, VCR, CD, video game, DVD player, retro, smoke alarm, camera, remote control, garage door opener, security system. In consumer, like toys, answering machine, camcorder, music instruments, swing machines, exercise equipment. In connectivity, like cable TVs, cable modem, router, switch, hub, firewalls, etc. Now, if you want to choose any type of microcontroller, you have to check the following things. The speed of that following microcontroller, the packing means it dips or its QFT or another type, which type of packing it's being used, the power consumption of that microcontroller, the amount of RAM and ROM provided on the chip, the number of timers and IO pins on that chip, the cost per unit of that microcontroller, the availability of compiler, simulator, and debugger of the microcontroller, and the availability of that microcontroller in a market. The AVR microcontroller family is a basic architecture of AVR, which was designed by two students of Norman Institute of Technology (NTH), Elf Illig Pons and Versh Woolen, and then was bought and developed by ATML in 1996. The AVR stands for Advanced Virtual RICS. The AVR is an 8-bit RICS single-chip microcontroller with Harvard architecture. RICS and CISC. CISC, a complex instruction set computer. A large number of instructions, typically from 100 to 50 instructions. Some instructions that perform specialized tasks and are used infrequently. A large variety of addressing modems, typically from 5 to 20 different modems. A variable length instruction format. RICS, reduced instruction set computer. Relatively few instructions, relatively few addressing modems. Fixed length, easily decoded instruction format. Harvard and non-Venom architecture. Von Neumann architecture. The same bus is used for accessing both cores and data. Pentium processor is based on von Neumann architecture. Harvard architecture is separate buses are used for accessing the code and data memory. That means that we need four set of buses. A set of buses for carrying data into and out of the CPU, a set of address buses for accessing the data, there are data buses for carrying code into PC and address bus for accessing the code. This is easy to implement inside an IC chip such as microcontrollers with both ROM and such data RAM are internal on chip and distance are on the micron and millimeter scale. Here you can see the Harvard architecture and von Neumann architecture again. A separate buses are used to transfer data from data memory to code memory and same data buses are being used in von Neumann architecture. Here is the diagram of AVIA microcontroller and family, how it's connected to CPU. And this is a block diagram of ATM Mega 32 block 32. We see its grounds, its connections, its ports, etc. The AVIA family. Uh, the AVIA family can be classified into four groups: 32-bit, X Mega, Mega, and Tiny AVIA MCU. 32-bit AVR 8032. These are the world's most efficient 32-bit MCU. Program memory is 16K to 512K bytes. Package is 48 to 114 pins. Operating frequency is up to 66 MHz. Performance is 1.5 Mbps per megahertz. X Mega AVR 80 X Mega. The 81 AVR X Mega series is the most performance series within its family. Its programming memory is 16K to 384K bytes. Package is 32 to 100 pins. Operating frequency is up to 32 MHz and performance is 1 Mbps per megahertz. Mega AVR 80 Mega. These are the powerful microcontrollers with more than 120 instructions and lots of different spherical capabilities, which can be used in different regions. Designs. Smoke-free practices are following. Program memory is from 4K to 256K bytes. Package is 28 to 100 pins. Operating frequency is up to 20 MHz and performance is 1 Mbps per megahertz. Tiny AVR, AT Tiny. This group have less instruction and smaller packages in comparison to Mega family. You can design the system with low cost and power consumption using tiny AVRs. Some of the characteristics are follow. RAM memory is from 0.5K to 8 bytes, 2K, 8K bytes. Package is from 6 to 32 pins. Operating frequency is up to 20 MHz and performance is 1.0 Mbps per megahertz. In the table 1.3, some members of 80 mega family share the informations like 80 mega 8 is code ROM is 8K and 80 mega 16 is ROM is 16K and 80 mega 120 is 128K ROM and so on with timers 3, ADC is 8, input and output method 23 and EEPROM of 80 mega 8 is 512 bytes. Now we will get familiar with the AVR part numbers and how to know from which family or from which group it belongs. Look at the first one 80 mega, 80x mega 64A1. It is stands for ATML. X mega means the group X mega. 64A1 means flash is equals to 64K. 80 ATML mega means group for mega group. 128 number 120 shows it has 128K. 80 tiny 44 tiny means tiny group. 4 means 4K. 80 UC3L 80 ATML 32 UC3L means 32 bit group and 0256 means 256K. So that's all for today. Thank you.